Hello everyone, this is Dr. Young, and in this video we're going to discuss osmolarity, which is also known as total molarity or the osmotic concentration. So hopefully you remember what molarity is, right? That was just how many moles of solute were in liters. And we often ask questions like how many moles of compound did you put in solution, or if you have so many liters of solution, how many moles of compound did you add? And molarity is great for chemists, and it's great for simple solutions where you just have like one solute dissolved in something. You know, if I have a 1.0 molar solution of sodium hydroxide, then I can really easily figure out how many moles of sodium hydroxide I add depending on how many liters or milliliters of that solution I add. And we use things like that, right? We have like, 12 molar HCl, 12 molar HCl, or we have 1.0 molar solutions of, like I was saying, sodium hydroxide, stuff like that. This works well for chemists. And in previous videos, right, hopefully you saw we would do things like figure out like, well, what's the molarity if you take 2.5 moles of something and you dissolve it so that you make 1 liter of solution. We would say that, oh, that's 2.5 molar. And we did a bunch of problems like that. And again, if you don't have any idea what I'm talking about, go back and watch the molarity videos. Osmolarity is important and different because it talks about the total molarity of a solution, right? So for more complex solutions like your tap water, seawater, river water, and I will talk about IV solutions later, or like your blood, or the fluid inside your cell or outside your cells, right? These are more complicated solutions that have many different things in them. So it makes sense to talk about the total molarity of all of the things that are dissolved in there, right? So we're going to include ions. We'll talk about ionization or dissociation in a second. And for when you have multiple solutes, for like all those examples I just mentioned. What's going to be crucial is that we have to use osmolarity when discussing osmosis. We need to know the total number of particles that are in each side of that semi-permeable membrane so we can figure out how water is going to move. Is water going to move inside a cell, outside of a cell, or to one side of a membrane versus the other side of a membrane? Now, if you have no idea what osmosis is, again, maybe you should go look at that video, but basically it's just the movement of water across a semi-permeable membrane, and it's based on differences in concentrations across that membrane. And so cells are a great example of that, which is why we're talking about it. Now, with osmolarity, right, if I had an example here where I have 2.5 moles of glucose and 1 mole of sucrose and 3 moles of sodium chloride in 1 liter of solution, what's the osmolarity of that? How many total particles do we have from this? And we'll talk about how, like, well, all you do is you just add them up. So I'm going to say 2.5 plus the 1.0 plus, and we'll get to this. This is actually 6.0 because of the sodium chloride here. And you just add that up to get 7, 8, 9. And we'd say this is 9. And then we'd say that it's osmolar. So osmoles per liter. That would be our answer for this. And so we're going to do a few examples so we can all figure this out together, right? That would be the osmolarity of this solution. Now, just to kind of remind us what we were doing before, right, with molarity, where we said we just had moles of solution, or moles of solute over 1 liter of solution, we had examples of, okay, well, let's say you have 2 moles of methanol in 1 liter of solution, right? And the idea is if you take methanol here, CH3OH, right, we said that if you look at methanol, it's got some partial charges, partial negative, partial positive, because of those polar bonds. And when we take methanol and we toss it in water, for example, right, we're mostly just looking at aqueous solutions here. When we take this methanol and we toss it into water, it doesn't break up, right? It stays the same thing. This is a covalent compound. So covalent compound. And remember that we know that it's a covalent compound because it only has carbon, hydrogen, and oxygen in it. Those all have very similar electronegativity, so it's not ionic. And when you take these ionic compounds and you dissolve them in water, they stay together, right? It doesn't break up. It's not like a carbon pops off or a hydrogen pops off or anything like that. We just take a look at this, and you've probably seen these, this type of drawing before in my previous videos. But if you take a look at this, the idea is that it just kind of gets surrounded by water molecules, right? The oxygen gets close to the positive things, so you have that. In this case, hydrogen bond. The hydrogens, which are partially positive, get close to anything that's partially negative, etc., etc. Right, so you just have these sort of attractive forces here, right? So positives and negatives attract. But the point is that covalent compounds do not dissociate. They do not break them up when you put them in water. They just get surrounded by water, but they stay intact. So I'll put covalent compound here, and I'll say does not dissociate in water. So if I have, right, let me write this out a different way. Another way to express this is that if I have methanol and I have the pure liquid and I put it in water, it stays methanol. Nothing changes about it. Only now it's aqueous. We've dissolved it in that liquid. And if I had, right, if I had, like I do in this example, if I have 2 moles of it, 2.0 moles of it, when you dissolve it, you still have 2 moles of stuff, right? It doesn't break into pieces. It's like taking 12 rocks, throwing them in a river, still 12 rocks, right? It doesn't become more rocks or anything like that. Now, this is actually different if we're talking about an ionic compound. So if I look at an ionic compound like sodium chloride, right, remember that sodium chloride is going to end up looking something like this, right? It's a crystal, so we have these alternating patterns of ions. I'm not going to draw a million, but you just want to jog your memory, right? We have all of these ions hanging out next to each other because they have opposite charges. So ionic compound, and again, we know this is ionic because sodium and chloride have very different electronegativities, so it makes an ionic compound. Now, if I take an ionic compound and I throw it in water, hey, we're going to see a very different thing happen. And again, you might have remembered this from previous videos, but if I take sodium chloride and I throw it in water, it doesn't stay together, right? So what we don't see, let me draw this over to the side. What we don't see happen is we don't see sodium chloride. Let me draw it in here just to make the point even more. What we don't see is we don't see sodium chloride still snuggled up next to a sodium chloride and then getting surrounded by water. What happens is that the sodiums and the chloride ions separate and move apart, right? So we don't see them stay together. They separate and move apart, and then water surrounds them. And again, right, the negative, partially negative part of water, the oxygen, hangs out near the positive things. And the partially positive hydrogen on water hangs out next to the negative things, etc. So you get all of those little attractions again from the oppositely charged particles. So what's different here is that the sodium and chloride are separating from one another, which we call dissociation. So ionic compounds do dissociate in water. Which is going to be really important for us, especially when we talk about osmosis, is that they're going to break apart and become more things. And so if I wrote this as an equation here, right, I'd say, okay, well, I have solid sodium chloride, right? If you take this and you throw it in water, the idea is that you're going to have sodium ions now, and you're going to have chloride ions now, both dissolved in water. So I'm writing aqueous here. So you're going to have them both in water. So the one becomes 2. Or in other words, what's kind of weird is that if you have 2, let me use a different color here. If you have 2 moles of this sodium chloride, it actually now becomes 2 moles of sodium ions and 2 moles of chloride ions, or in other words, it becomes a total of 4 moles of particles. Right? It breaks up. It breaks up into 2 pieces. I kind of use the analogy of, like pens with caps. If you have 12 pens with caps, it's kind of like you can imagine you really have 12 pieces, right? You have 12 pen bodies and 12 caps. You might refer to them as being 12 pens, but really you could break them all up. Or sorry, you might refer to them as 6 pens, but you could break them all up and you have 12 pieces because you have 6 pens and 6 caps. They break apart. You can make them into more things. And that's kind of what's going on here when you dissolve ionic compounds, is that those ionic compounds break up into however many pieces they're made out of, and it now counts as more. So we would say that the molarity would be would be 2 molar, but the osmolarity would actually be 4.0. It'd be 4.0 osmolar because that's telling us how many particles there are altogether. So let's take a look at 5 examples here, right? So for this first one, the idea here is that I've got solution A just has glucose, right? So I'm looking at single solute examples, and I want to know what the osmolarity is of these solutions. So for solution A, I've got glucose. The important thing to notice here is that glucose is covalent. Whoops, if I can spell covalent. Glucose is covalent, which means it does not dissociate. So I'll say doesn't dissociate. So that means if I dissolve for every 1 glucose molecule that goes in, I only get 1 particle out. So there isn't, right, there's only 1 particle. That's how many particles. And if I take 1 times 1.5, that means that my osmolarity is 1.5 osmoles per liter. That's the osmolarity. It doesn't change. The osmolarity and the molarity is the same with the covalent compound because they do not dissociate. Now that's different if I have like KBr, for example, is ionic. It's made up of ions, right? I know that KBr is made out of K plus and Br minus. That's 2 particles, so I'm going to say 2 here, right? Because again, that's the number of particles. So really, if I have 1.5 moles of 1.5 moles of potassium bromide, really I have to multiply it by 2 because there's 2 pieces, 2 ions in that potassium bromide. Or in other words, this is 3.0 osmolar. All right, so I doubled it because that's how many pieces there are. Barium chloride, for example, is, Barium chloride is also ionic, and it's made up of a Ba plus 2 and a Cl minus and another Cl minus. So it looks like I have 1, 2, 3, right? BaCl2. I have 3 particles here, so guess what I have to multiply this by? 3. So then I just go 3 times 1.5, so now this is 4.5 osmoles per liter. And you just do that every time. If you have a single compound dissolved in a solution, if it's ionic, you need to multiply that total molarity by the number of particles that it breaks into. So sodium phosphate, for example, you can see where we're going here. Sodium phosphate, I've got 3 sodiums, because that's what the 3 means. So I got sodium, sodium, sodium. And phosphate's not many things, right? Remember, it's 1 polyatomic ion. It's one thing. It's this phosphate. So it looks like here I've got 1, 2, 3, 4 particles, so times 4, giving me now 6. So the osmolarity of this solution would be 6. Now remember, the molarity of these solutions is all identical, because that's how many moles of that whole compound you put in. But since some of these break into more pieces, the osmolarity changes. The osmolarity is a different number. And then lastly, urea here. Again, you'd look at this, is it ionic or not? In this case, it's not ionic. This is covalent, which means it's not going to break up, so it's still just the 1 piece. So this molarity this osmolarity is the same. So we can take these single solute examples, and the biggest thing to keep in mind is that an ionic compound is going to break up. How many pieces is it going to break up into? Depends on the ionic compound. Now let's look at a multi-solute example, right? So here's 1 solution. This is Ringer's injection. This is an IV solution. There's a whole bunch of different IV solutions that you'll learn about. But this is Ringer's injection, right? So this is all 1 solution. All of these things are mixed up. You have sodium ions, potassium ions, calcium ions, and chloride ions all together. And all you do is, if you know the molarity of each individual piece, all you do is you just add them up. That's all we're talking about here. You just take this and add these 4 all together. Right? You just add all these suckers up. And what you should get here, 0.310, I think. Just add them all up together. If you add all those molarities, remember that we're talking about the total moles. We want to know the total moles of particle. That means the osmolarity, if you take this whole solution, the osmolarity is 0.310 osmoles per liter. Or if you want to put milli, sometimes you see milli a lot. Actually, you see milli a lot. You could also say it's 310 milliosmoles per liter, however you want to put it. But either way, right, the total molarity, we just, again, want to know how many total particles are there dissolved in solution. So if you have a whole bunch of things, for example, in your extracellular fluid, your intracellular fluid, you just add up, okay, well, what is the concentration of sodium and potassium and phosphates and chlorides? And you just add up all of those things to get your total molarity or your osmolarity. Let's look at one more final example here. So here's something you might see in my class, right? Consider two solutions, A and B, separated by a semi-permeable membrane. That's your clue that we're talking about osmosis here. That allows water and small particles to pass through, right? So we're supposed to assume that none of the particles that we're talking about can pass through, just water. So just water passes through. And we want to know, does water move to the right or the left? Will water flow to the left compartment or the right compartment? And we're told what the concentrations are on the left and the right here, right? So I know, for example, that A here has this stuff in it. And I know that B has all of this stuff in it. So I need to compare and find out what the osmolarity is of both of these. So why don't you take a pause for a second, see if you can figure this out. This is actually both types of examples I showed you. One has multiple components, and one has an ionic compound. So I'd pause, see what you can do, and then I'll do it in a sec. So let's take a look at this, right? So solution A says that I'm 0.1 molar in lactose and 0.05 molar in urea. It tells me that both are electrolytes, but I could also just Google them and see that they are covalent compounds, so I know they're not going to dissociate. So in this case, I just need to add them up. I just need to take 0.10 molar for the lactose and add it to the 0.050 molar for the urea. And now I know that this is 0.15 molar, or I should say osmolar, actually. Right? Osmoles per liter. So that's the concentration. That's how many particles are on the left-hand side. Now, if I look at the right-hand side, it looks like I'm 15 or 0.15 molar in potassium chloride. It tells me it's an electrolyte, or in other words, it's ionic, right? Remember, electrolytes are ionic compounds. So that means I need to see how many particles potassium chloride breaks into and multiply that by my 15, right? So I know I have 0.15 molar, but potassium chloride is made up of two ions, right? It's made up of potassium and chloride. I've got two things. So that means I have to multiply that by 2 to get 0.30 osmolar. So these are the two that I'm comparing. I've got 15 or 0.15, I keep saying 15, 0.15 or 0.30. Clearly the 0.30 is higher in concentration, so that's where the water goes. And again, if you haven't learned about osmosis yet, don't freak out too much, but you should be able to figure out what the osmolarity is of these two solutions. If you do know what osmosis is, then you should know that water always moves towards the side with with higher concentrations. So in other words, this would move to the right compartment, would be the correct answer for this question. So hopefully that gives you a couple of examples. Hopefully you have a better sense of what osmolarity is, right? It's just the total molarity of particles for complex solutions or solutions that have ionic compounds in them. Really useful. In fact, it's necessary if you're ever talking about osmolarity. So study up, do some practice problems. Please leave any questions or comments down below. Happy studying.